a week or so more, because then we'll have been together for almost a month. But just a reminder, engagement rubric points, right? You get 3 points a day by showing that you are engaged in the process of our learning. So that ways that you do that are, number one, you don't get your cell phone out at all, at any reason, at any time. Obviously, unless there's an emergency, then you can talk to me later, okay? Every time you pull it out, you'll lose that point. Second thing is discussing when it's time to discuss. When I say talk to your table buddy about it, that you do, right? You don't just like sit there quietly. Like, you gotta discuss in that process. But on the opposite side, you're not discussing when it's not time to discuss. Okay, so if I'm still teaching, you can't be talking to your neighbor, even if it's relevant to what it is, because you're distracting somebody from what needs to. Just hold on to it. There'll be moments, as you've hopefully seen, where I give you time to talk during class. Okay, we've been doing great so far, so there's like, I'm not saying this as you've been doing awesome, but just as a reminder as we keep moving forward. Okay? All right, today's objective probably is going to make no sense right now because we haven't learned what these words even are, but that way it just gives you an idea of where we're headed. So our goal is I can determine an empirical and molecular formula from data. So we got a lot of math going on with us today, so leave your calculators out of calculating these things, okay? And that's literally all we're covering today, and your homework is just one worksheet in your packet, practicing it some more. So no AP classroom quiz or anything else like that. So let's start with definition-wise of what they are. Hi, guys. Okay, no minding you. Let's start with the definition of what molecular and empirical are, and then we'll get to the math side of things. Oh, come on, guys. Okay, so like I said, chemistry triangle, we want to bring it all to life. Okay, so this right here is your first exposure, at least in this class, to a chemical equation reaction. Okay, so let's break it down from all three sides. When I say symbolic, that would be like alphabet soup. MgO2 to MgO. Okay, like that's one way to represent the equation. Molecularly, what we can't see, often in chemistry, we use bouncy balls or circles. It's not truly what an atom looks like, but it still kind of gives you an idea of what's going on. So this is what magnesium at the molecular level could look like by an atom, because it's just a singular thing. Oxygen is one of our unique ones, and we'll learn in a later reason why, but it doesn't actually exist as just O. It always exists as a pair of O's together, so we call it O2. So whenever you take a deep breath, join me. Right, you're breathing in O2 molecules, N2 molecules, and lots of other stuff too. But oxygen always comes in pairs, okay? Then they bond together to make this thing called MgO. And now we have these little lines that represent the chemical bond. I think of them once again as little Legos. When they become a molecule, the Legos are now stacked. They're linked together, they're connected, and it's a pretty hard link. Like, it's not something you can just pull apart easily. It can be broken again, but not easily. So now let's see this with our eyes. So this is magnesium, right, like we said. What are we reacting it with? Oxygen. Where would I get some oxygen from?
The air.
Perfect idea, right? So lots of oxygen in the air. Where did my plants go? Here they are. Okay.
I'm not wrong.
Write them off here a little bit. Okay, so I'm going to hold my magnesium. We got oxygen in the air. Ready, set, go. Do you see it? Okay, so it is happening, but like crazy slow. So some reactions take a long time, like years of time, which we don't have time for. So we are going to do it though. We're just going to use something to help speed it up. Okay, but I want you to recognize like this would happen without it. It just would take like years and years and years. Okay, so we're going to use heat, fire, to make this process go faster.
Yes.
Okay, what I want you to notice the individual Legos right now. So Lego number 1, magnesium. Notice how it looks, its properties. Lego number 2, oxygen. Notice it, its properties. Okay, we're going to combine them. What I want you to notice is what is it like when they combine? Okay, is it like a child of the two? Right, where like my child, like Emery, my daughter, has like Juwan's eyes, but she has like my skin, right? Is it something like that where you can see both? Is it more like one than the other? Okay, how would you describe the end product based on the before? That's what I want the discussion after to be about, okay? Everyone understand what you're kind of thinking about as you observe? Okay, now, this reaction, as I light it, produces a very, very, very bright light. which is not healthy to stare straight on at. It's like you shouldn't stare directly at the sun. Okay, so here's how we'll do it. I'm going to hold it right here. If you look at the letter O, you'll still see what's going on. But then you're not staring straight at it. Does that make sense? It's not good for your eyes. Here's your warning, okay? Okay, I know it's tempting, but you'll still see it, I promise. Just give it like a little side glance. Takes a second for it to light, but once it goes, you'll know the difference. Oh. Just stop staring straight at it.
What if I want it?
Okay, now I'll bring it around so you get a closer look to see our end product. So this is now magnesium oxide, our end result. After I pass you, turn to your table, buddy, and discuss how would you describe them. When the Legos stack, what's the result?
Shows people. Is that fuzzy?
It's a little out of focus.
I'll touch it after I get it around. It's probably calm my ears. But it does burn so quickly, it's not like. It is harmless, I mean, I guess anything we create is the right way. So what I'm going to do here, I took it around like this so you can see it. But actually it's like very fragile. And it's like almost like it's a powder. So I can crumble it up like chalk. It kind of holds its shape like right after it burns. But like all that white stuff on here is also magnesium oxide. Okay, so what's our conclusion? Is a molecule like the elements it's made of?
I mean, powder is just reusable solid. So technically,
Like, but pretty far off, right? Like, I mean, you can stretch to find similarities.
you have these powder that shape
Right?
within that powder.
But like, this is what
So
makes
it's
chemistry
the
so
solid of the
cool.
magnesium and
It's like you can take two things and turn it into something that's totally different by just the Lego stacking. Water's another great example. Hydrogen, explosive. Oxygen, explosive. What do we use water for? To put out explosions. Like, but they're created from these things that are crazy explosive, right? So as we go through it, that's kind of to give you once again that connection of what we want to do with our triangle, of connecting symbolic, what can I see, what can I see, how does it all fit together, okay? It has a lot of stuff in it too that like keeps it from being explosive because it's not pure oxygen. But if it was pure oxygen, yeah, don't light a match, we're in trouble. Yeah, exactly.
Bonded to one of the noble gases. Is that why it doesn't burn?
Like, in what way?
Is that what makes it less reactive?
Part of it, yes. But not always. Sometimes something doesn't have a noble gas and it can still be very stable. But yes, that definitely, when we get to our bonding unit, that plays a role for sure. Okay? Alright, so with these two words here, everybody, we have what is known as the empirical formula and the molecular formula. Here's like this is like an official definition of what it is. Here's how I think about it in like Miss Alviso's simple brain kind of way. Okay, the molecular formula is the thing. Okay, water's molecular formula is H2O. It's what it is, it tells you its identity. If it's H2O, it's water. If it's not H2O, it can't be water. Like, that is its identity. An empirical formula is simply a mathematical operation which reduces down to see what's the ratio of these things. So in water, its empirical is still H2O, because you can't reduce 2 and 1 any smaller. But other molecules, and I'll show you an example here, can be reduced. So for example, this right here, label it. This right here is vinegar. This is the chemical formula for vinegar, ascorbic acid. Okay? C2H4O2. That's what it is. If I have this, it's vinegar. If you change one of these by one number, if it was C2H3O2, not vinegar. Right? Like, it changes what it is when you change what's bonded. Okay? Now, mathematically, since it's a 2:4:2 ratio, I can simplify it and say, oh, there's a 1:2:1 ratio for the empirical formula. First thing, notice, we don't write number ones in chemistry. You can, like, it's fine, but it's not necessary. Okay? But this is not vinegar anymore. You can't call this vinegar. It's not vinegar. It's just vinegar's ratio. Now, this actually is its own thing. It is a completely different molecule. It's known as formaldehyde.
Oh,
You know what formaldehyde is used for?
sounds dead.
Yeah, it's like what they preserve dead things with, right? So like when you do a dissection, you're often smelling formaldehyde. Okay? But like formaldehyde is not vinegar. Right? You don't want formaldehyde in salt chips. Bad idea. Okay?
Good flavor.
Not good. Okay? But in a sense, it has the same empirical as acetic acid does. Okay? So if I'm given this, the molecular of something, and we're asked for the empirical, it's very simple, because you simply just reduce it down to the wholest ratio. So C6H6 would be just CH. That would be its empirical formula, because it's the simplest ratio, right? We say for every one carbon, there's one hydrogen. But this is not this. And this doesn't even exist. There's no molecule that is CH. It doesn't bond that way ever. It's not stable. We'll talk about why, but like it just isn't a thing. If I'm given an empirical and I want to find the molecular, why is that harder to do? Brian?
It's like, with like the C, if you were just given like CH and you wanted to get to C6H6, you wouldn't know like what to multiply it by, because it could be like C2 and H2.
Yeah, like it's infinite in a sense, right? Like this could be P4, oh, not H. Adding in things that don't exist. P4O10, right? Like if this were double it. But it could also be times by 3, right? P6O15, right? It could be, we'll be exaggerating here, but it could be like times by 11, right? If that thing exists.
That's my favorite.
Right, so you can't go this way, but this is the information we want without data. So keep in mind that an empirical formula is only a stepping stone. They're quite pointless if you're not trying to get to here. Because like, okay, why do I care? Like I can see from here it's a 1-to-1 ratio. Why do I need to list it? But what we're going to find is that when I have an unknown substance, the process to get to here requires finding this first. So that's where it's going to come in handy. So that's the next thing we're going to be doing is finding an empirical to get to a molecular. In a sense, this is what a chemist does, or a scientist or a forensic scientist does when they find an unknown. Unknown substance, have no idea what it is. I can use this exact process to determine what my white powder is, because there's a lot of white powders in the world of chemistry. And you maybe want to know what it is. Okay? All right, questions so far on just definition of empirical versus molecular. Now we're getting to the math side of things. Okay, now, just like last time, I'm going to be using different colored markers very strategically to follow my steps. I encourage you to do the same. Okay, hopefully you found it helpful last time. If you didn't do it last time and you're still confused from last time, maybe try my method this time and see if it helps.
What element is 40.92%?
Oh yeah, that carbon is what's supposed to be after that percentage. So add that in first, everybody. So this right here tells us ascorbic acid contains 40.92% carbon, disappeared. Okay, 4.58% hydrogen, and 54.5% oxygen buying mass. This data would be determined through a mass spectrometer. So if I put my random white powder into my mass spec, we saw the isotope graphs it can give you, but it can also give you this data and say, hey, there's this much carbon in it, there's this much hydrogen, this much oxygen. Our goal, once again, it's always good in mind. Keep in mind, what's the goal? Where are we headed? Otherwise, it just feels like you're doing this, okay? So the end goal is to get the empirical formula, which means we want to know C what, H what, O what. That's the goal. What is that ratio in the end? Now, step number one I'm going to do in red, okay? With our goal, let's compare that to what was given. What type of data or values or units is given? Percentages by
mass.
mass. So I'm in percent by mass. What type of unit are subscripts? What relationship do those numbers have to each other? Yeah, Nancy. Yeah, it's like atom by atom, right? For every 3 carbon atoms, there's this many hydrogen atoms. Good, have a sign base. Which atoms is proportionate to a mole. So that's where we're going to go, is we're going to go to the mole because the mole will show us that simple ratio. Okay, so step number one is with whatever's given, because you can be given a variety of starting things, but the objective is the same. So take what is given and convert to moles. Okay, so step number one is we're going to take whatever they give us and we got to convert it to the mole. So I'm given percentages by mass. We know how to go from grams to moles. So we're just going to make a quick switch and change our percentages to grams by just saying, let's assume we had 100 grams. Because if I do that, then my percentages just become gram amounts. So whenever you have percentages, just assume 100 and change the percentages into grams. Okay, so I have this many grams of carbon. Leave a little space because we're going to do multiple conversions here. Okay, so I have that many grams of carbon. I have 4.58 grams of hydrogen and 54.50 grams of oxygen. Okay, we're trying to convert them into moles. So let's start with carbon. It's in grams, convert, set up your fraction. The bottom of the fraction should be what I'm trying to change. So grams of carbon into moles of carbon. The mole and gram relationship is always the periodic table. So 12.01. Okay, I plug that into my calculator, so it would be this divided by this, and I got 3.407. Now, it's up to you, but something I recommend when I'm doing like an example problem on the board, I will have done all the math prior. So I recommend don't worry about trying to type it in. Just focus on like understanding the process, because then we'll do a practice problem in a second and you can practice doing all the typing in. But that way you don't get like distracted and you're typing something in and then you miss like the next step. Okay? All right, moles of carbon, check. Let's get to hydrogen. So hydrogen, very similar. So molar mass is 1.008 is what I think is on your periodic table. So 1 mole of hydrogen. When I plug that in, I got 4.54. And then last one. Let's get hopefully you're feeling the repetition here because it is very repetitive. We're just now going to moles of oxygen. So for oxygen, it has a mass of 16 for every one of them. And I got 3.406. Questions or confusions on step 1? Once again, if a number ever feels magic, like she just pulled that out of a hat, ask where it came from, because I promise it's not magic. Like there's a logic behind it. Okay, step number 2. Oh, that marker's struggling. Okay, step number 2 is, we're into moles now. Once again, keep in mind the end goal. We now need to know what is the ratio. If I have one of these, how many of these I have, like the simplest ratio it can be. So I'm going to take whichever one is the lowest and divide it by the rest to get that whole number ratio. Okay, so we're going to take the smallest mole value. And divide the rest. Once again, a ratio is just a fraction. It's just saying if I have one of these, how many of these do I have? So, smallest choice by barely, be our oxygen, right? So I'm going to divide all of them by this same number. Okay, so when I plug each of these in, this one pretty much gives me 1. This one I got 1.33. This one I get 1. Questions on step 2? Now, sometimes after step 2, you'll be done because you have your ratio. For every one of these, there's one of those. For every one of these, there's 1.33 of those. And that's where this one needs some fixing. If these are whole numbers, or really close to a whole number, let's say if it was like 2.01 or 2.0 something, like that's close enough to say 2. Or if it was like 1.9, we could round it up to 2. But 1.3 is not close enough to round. So what we need to do is we need to change our ratio so they are all whole numbers. Anyone by raise a hand have an idea how I could do that? Yeah, Evan, what do you think?
Multiply all of them by a certain number until they're all close or at a whole number.
Good. Do you have a guess of how I know which number to pick?
Multiply it by 3.
Why?
Because if you multiply 3.33 by 3, it gets to 0.99, which is the closest you're going to get to a whole number.
Yeah, well done, Evan. So what he's looking at here is the decimal that follows my whole number. 0.33 translated to a fraction is like a third. And so if I multiply them all by 3, you gotta do it by all of them because we don't want to change the ratio. We just want it to be a whole number. That ends up working out that these just changed to 3. This is 4. And now you have your balance. So our answer would be C3H4O3. So putting on our steps here. So step number 3 is if needed. Once again, if you already have whole numbers, don't do anything. But if step 2 didn't result in whole numbers, you can put quotations around whole, because like it might not be exactly a whole number, but should be really close to one. Then multiply by factor to get there. And in this level of chemistry, your options for number 3 are very small. You're gonna either multiply it by 2, because it's a half, like it was 1.5, so you're gonna double it, or you're gonna multiply it by 3. That's really it. It can get more complicated, but in this level, like if you have to multiply it, so if by chance this is looking super weird, and it's like, I don't know, 0.4, like I'd maybe backtrack and check your math, because normally you just made a mistake somewhere else. So, yeah.
I just have like one question on stuff like, why would you multiply it by the smallest number, like by the smallest number? Like how would you know like why to do that? I was just curious.
So we're always gonna divide by the smallest to get that ratio. So we always have that comparison, okay, for every one of these, how many of these do I have?
Okay, so you just like want to get the smallest ratio like first, and then you can compare
Yes.
everything else to it. Okay,
Yes. Does
makes
that
sense.
help?
Yeah.
Okay. Any other questions on our steps here? Now, don't say anything out loud. Give me a thumbs up or thumbs down. Is this ascorbic acid? Yes or no?
What?
Is this what we found? Can we call this ascorbic acid? Yep. Or no? Is that, based on our question, because we had the data for ascorbic acid, is that ascorbic acid? The answer is no, it's not. Is someone willing to share with us their thoughts of why? Yeah, go ahead, Brian.
Well, we were just trying to find the empirical formula, so, that's just the ratio of, ascorbic acid, so we don't know if that's actually, like, how it's made.
Yeah, it could be, because sometimes they're the same, but if we've only gotten to the empirical, it's just telling us the ratio. That in ascorbic acid, for every 3 carbons, there's 4 hydrogens and 3 oxygens. So that's our next step is now, let's get to the real theme of what is ascorbic acid. Garrett.
I'm just confused, like, why are you able to convert the percents into, like, grams? Like, what is that, like?
So it's the idea of the percentage is by mass, so it's already a mass relationship. And so if I just say, let's assume we have 100 of something, then the percentage will equal that exact
Okay,
amount.
that makes sense.
Does that make sense? Yeah, good clarification of your question. I was might be too fast. Any other questions before we do the next step? Okay, move on down below. This second part B is much easier, by the way. Like A takes the most work. The second step is actually much easier once you have the empirical. Okay? So this now says for ascorbic acid, the experimentally determined molecular weight is 176. Our goal is what is the molecular formula? So now we want to go, what is ascorbic acid for real? Okay? Fun fact, ascorbic acid is vitamin C. It's chemically important. So, all right, let me get rid of this first. Okay, so rewinding here, Brian, I'm going to bring you back because I think you were the one who said it. So earlier we said if I was given an empirical, why is it difficult to go to the molecular?
Because like we don't know like how much molecular is. We don't know how much of each atom that we have.
Yeah, thank you for reiterating what you said earlier. We don't know, is it times by 2, is it times by 3? That's what this is going to help us figure out. We're going to figure out, okay, do I need to times that by 2, 3, 10, 11, 20, whatever, okay? So the equation we use is we're going to set up a ratio of the molecular mass. Okay, that's how much the real thing is altogether. And compare it to the empirical formula's mass. Because in a sense, we're going to compare the whole to the part and see how many times we need to multiply to get it there. Now, this on top has to be given in the problem. You can't find this. I mean, you could, but you'd have to go do an experiment on a very complicated machine to find it. Like, it's not just something you come up with. It has to be given. Where does this come from?
From the grams of the people.
Yeah, right, we have the formula, so now we can just add up. So this is where we're just gonna add up the empirical formula's mass. which we calculated prior. So when I added up 3 carbons, 4 hydrogens, and 3 oxygens, I got a mass of 88.01. So this came from just adding up these guys.
Oh, okay.
The top number is the one the problem gave me, so 176. Divide it. I got pretty much 2. Don't circle 2 because it's not your answer. What do I do with that 2?
You multiply it by the empirical.
Good, there. Yep, so now we're going to multiply this by the subscripts to get C6H8O6. And that is ascorbic acid.
Huh.
I like that. Huh. That's cool. Spent 30 minutes solving a problem.
Science.
Yippee! Okay, questions right now? Yeah, Christina.
How is the molecule weight different from the molecular mass from the 88?
Ask that one more time.
How is the 170 different from the 88?
So this is the mass of the actual molecule. Like, if I were to add this up, that's how we get the 176. So if I add this up, I get the 176. But in a sense, we didn't know this, so we used the 176 to get us there.
And the 88.1 is would be the same as the 88.
Yes, yeah, it's that simple. Does that make sense? Okay. Yeah, Jane. Yes, so I just added up 3 carbons, 4 hydrogens, 3 oxygens, and yeah, that's how I got my case. Any other questions? Okay, turn the page. I'm pushing you in the swimming pool. Time to swim. Try the next one with your table buddy, and let's see how we do. Ready, set, go.
So HF is.
I'm not going too fast, I'm just writing what we know.
The what? Should that take that one is small. Wait, so 60.
Once again, talk it through, even if you're talking to yourself. Okay? Make the pathway deeper because of understanding, not just copying.
And then above that is 1. And then,
Wait, so you did that, right?
yeah.
Oh, yeah.
So 62, so it would be 62.2 divided by 178.4.
It's like these are like the best non-graphic
0.35.
order of operations.
Is that a pound?
Again, don't just copy the why, make sure you understand why you're doing it. When you're done, set your pencil down so I know you're finished.
But yeah, that's just one.
And then we divide both by 35? Oh, 0 by 35?
Yeah.
Right?
I think so. Is it 3? So it'd be 1.
You don't have to.
So it'd be.
I mean, you can try. But it has a, there's a twist. It's not exactly.
I don't know if I want to do it anymore.
Oh, yeah.
Is this like I use this
That one's safe enough to say.
so what does that mean?
Oh, it's this question.
Like it's a lie.
Wait, so it's not connected.
Not just like a verbal lie. Like, oh, that's icy.
Wow, I'm sorry. We're doing great.
Yeah, that's like the
So we're in here.
Tell me how you just had 0.35 and 1. Oh. Would that work every time?
so
I can see why it works this way. It definitely could be a lot trickier here. That's what it could be like. It could be hard to see like.
so I think we're
But I
trying to
think
find
it would, because the idea of it's just like, this is your issue. It's a 1 to 3.5. We just want it to be represented as a number, like dividing by the same. So I think if you only have 2.
but I think the way we find it is because burning it like
Because you're still in the logic of like, what is the ratio, right?
so if you do 0.5
Yeah, we'll talk about the next one has a twist. You can look at it, but it's not.
You can't have anything without burning.
and then
How are we doing over here?
It's a little different, so we will do it. But if you want to start thinking about the end of Okay, I think I estimate my way around and checked everybody's, and everybody's right. You should have HFCl3. Have a smiley face, everyone. Well done. Any questions or things that came up as you were going through that process? Yeah.
I know what order to write it in.
Oh, good question.
is it alphabetical?
As of right now, I really don't care. Like, all I care is that you got the ratio. A simple answer for now until we learn more about bonding is you can actually follow the periodic table left to right. Meaning if it's more to the left, it goes first. The more to the right, go after. That rule like works 80% of the time. So that one you can use for now. But, good question then. I don't know. It's pulled out of my head. So. Okay, any other questions? All right, let's look at the next one together, which I love some of you are already glancing at it. Hopefully you're recognizing it's a similar question, but there's a little difference. But keep the similarity, right? Like as you're imagining your brain, like I think it's valuable to like, I don't know if you can quite feel it. I wish we could feel the pathway we need to build. Maybe we can. Sometimes your brain hurts when you're thinking really hard, right? But like, just like trekking through snow, right? Like the first person trekked through, it's the hardest. The second time gets better, third time is easier. Like that's once again why you have to do your homework. Because if you only trek through the snow once, you're gonna come back next Tuesday and the path's gonna be filled back up with snow. And you won't remember it. Okay, you've gotta do the homework to pound that down, turn it into pavement. Right? I'm gonna pour cement into your pathway. Okay?
So we're putting the cements on the snow?
Yes.
After you've made the path.
Oh,
Make the path.
but the snow's still there.
That's fine.
Think
about it.
I guess we're shoveling the snow, not just stomping it. How
What
about
if the
that?
little mountains would get all the snow shovels out, fall back onto the path?
And then you shovel it again.
My shovel.
Okay, so there's another method for getting the same information, but it gives you different data, and that's what we're gonna look at here. It's known as a combustion analysis. The difference is, in the first one with a mass spectrometer, it just gives you straight up percentage data. This much carbon, this much hydrogen, this much oxygen. In this type of data, it's not as clean, but the idea is still the same, right? So as you're building your pathways, recognize the similarities of this path with the one we just did, but also recognize the differences. The basic idea of how combustion works is you take your sample and you burn it. Okay, so here's this little gray rock represents my sample. I burn it. In the process of burning it, number one, you have to have oxygen, right? Things don't burn without it. And so oxygen gets sent in there to allow it to burn. As it burns, all things in a combustion analysis process break down into carbon dioxide and water. Those are always present in every fire. The end result could have more things besides those two, but those two are like always there. And so this, how would I say it? This experiment setup collects the water that was created and the CO2 that was created, and then that's where, let's go to our data here, these numbers come from. So it's telling you I'm burning this thing, CHO, once again the goal's still the same. The difference now is what is given. But we're still just wanting to isolate the moles of each. So what part of my data could help me isolate the moles of carbon? After it burned, where did the carbon go?
CO2.
Into CO2. So we're going to take the value of CO2, so the 0.561 grams of CO2, and we're going to isolate just the carbon, because that's, once again, in our formula, we care about moles of carbon. Okay, so first step, the bottom should always match where you're going from, so grams of CO2. I'm going to convert it first into moles of CO2. A rule with conversions that it'll make, you'll see it here and you'll see it a lot more, is that if the unit is different, the label has to be the same. Because you can't compare 1 grams of one thing to moles of something else. Okay? You can't say, how many pancakes does a dog weigh? Like, you could figure it out, but there's not a direct connection between them. Okay? Alright, so this is grams. How do I find the grams of something? Yeah, so I did that and found it to be 44.01. Okay? Now, we want to pull out the carbon from the CO2. So in 1 mole of CO2, now notice, since it's moles, you can compare it. I can compare a dozen things to a dozen other things because they're both a dozen. So moles can compare to mole. So now I'm isolating it down to just carbon. How many moles of carbon are in a mole of CO2? 1. Just 1. Okay? Now, I understand math. Okay, I'd say I understand it pretty well. I understand this fraction mathematically means nothing. 1 over 1. But understanding wise, like that is extremely important in your thought process of isolating just the carbon. Okay? Alright, I plugged that in, so I would just do this divided by that. And I got, that's wrong page. 0.0128 moles of carbon. Once again, notice in the end, we got to where we did before of just the moles of carbon. Okay, let's isolate just hydrogen. What would we choose to do that with?
Water.
Yeah, the water, because that's where it ended up. So we have 0.3 306 grams of water. We're gonna do the same thing but isolate the hydrogen. So for water, it's 18.02 grams for every 1 mole of it. Now I'm going to isolate the hydrogen within it, so every 1 mole of H2O has how many moles of H's? 2. There you go. So now it's 2 moles of H's because it's H2O. Plug that in, and I got 0.0340 moles of H. Okay, and hopefully it feels like similar, just started off a little different. This is probably the roughest part, is the oxygen. Bryson?
So just making sure I'm understanding here, with the 1 mole H2O, 2 mole H, it's just since there's 2 H's in there.
Yep, if I break down the water, for every 1 water,
Okay.
I get 2 H's. Yep, perfectly said. All right, anyone see the problem with finding the oxygen?
It's in both.
It's in both. There's also a third problem. You remember how we combust something?
We're introducing outside oxygen.
We also add oxygen to it. So some of the oxygen in those isn't oxygen we want. So you can't just do this process here and add them together, because you're going to have excess oxygen there. But that's why there's this information right here. They gave us the total mass of the sample I burned. This sample is made up of carbon, hydrogen, oxygen. So if I subtract the carbon and the hydrogen amount, I can find my oxygen amount.
Back to algebra.
Everybody see that? Okay, so my formula I'm going to use is the total mass of the sample minus the grams of carbon minus the grams of hydrogen, and that will give me my grams of oxygen. Okay. Now, check your units. Are these in grams? No, so we have to convert them there. Oh, so 1 mole of carbon, 12.01 grams. Sorry, welcome to full page chemistry problems.
Yippee.
Yeah.
Could you also find the moles of, oh, never mind actually.
Just answer your own question.
Yeah.
That's okay, I do that all the time. I'm like, oh wait, my grade says never mind.
Yeah.
Alright, so these I just got through doing that math. Sorry, I'm going a little fast with the numbers.
That's okay.
I just want to come to a conclusion before the bell rings. Don't want to leave you hanging. Okay, so now these are coming down here. The total. So 0.255 minus my carbon minus my hydrogen. And so I get 0.068 grams of oxygen. Good, Dylan, but grams aren't helpful to us. We need moles. That's still step 1. We're still step 1, by the way.
No!
What did we do on just
We're getting closer.
We're getting real close. Okay, so moles of O ends up being 0.0043
I keep writing it.
moles of O. Okay, step 1 is done with a few side steps to get there.
Only step 1?
But step 1's the longest, because then what's step 2?
Divide it out by
Divide by the smallest. Now, it's a little messy with this one because you have a lot going on, so you can choose, like sometimes I pull these out and just create new fractions. So I have, so here's my moles of carbon, 0.128, .034 and .0043. Kind of reset it back up. It's up to you how you want to keep track. So this is my smallest, so I'm going to divide that by all of them.
Oh, and then we have to divide all of them.
So I get 1.
No. I'm having a blast.
3 and 7.9, which we can call 8. So we get our empirical is C3, H8, O.
Shush. Be quiet. 7.2.
Is that our answer?
No!
But we're really, really close, because it wants the full deal of molecular, which is why it gave us
I'm actually gonna go cry.
60.1. So what do I need to do? I'm going to add this up.
Why didn't you warn me?
When I added data, I got an answer of 60.1.
Also,
Oh, you just added.
So we are done. We just didn't know it yet. So this ends up being the same as the molecular.
Whew. That sucked. That's great.
But if it didn't add up to that,
questions are we gonna have?
then it would be like times by 2, times by 3.
Oh, it's the same as.
Okay?
Okay.
Now, once again, that took a long time. We did like 3 problems in class today. Good job. Obviously, down the road, it can't take us this long to solve these problems. But that's where if you travel the pathway enough times, the pathway gets faster. But you've got to travel the pathway to help it get there. We've got 40 seconds left. Any questions before we go? Jonah? Yeah, go for it.
How many homework questions are we gonna have?
The problem is.
So there's only one homework that's like this. The rest of them are like the first one, which aren't as bad, right? You guys did that practice one in like 7 minutes or so. There's only one combustion.
And